Right, thank you very much. Got it. Yes, good morning. Very nice to be here. Thank you for coming to this presentation. Today we're going to be describing some of the aspects related to this project that we did for the California Strategic Growth Council. It's related to mobile biochar production for methane emission reduction and soil amendment. I have to say that nowadays everybody's talking about methane reduction, and the SGC was really visionary to actually put a proposal requesting a call for proposals requesting projects along this line. This is pre-pandemic type of 2019, and it was even before when we submitted the proposal. So really visionary of the Strategic Growth Council to do that. So yeah, we'll have a little bit of a presentation of the members of the project. So yeah, this project wouldn't be possible if we didn't have a fantastic group of people that worked. We have a number of researchers from UC Merced that were part of that. We have me, then we have Professor Asmeret Berhi, who's now at the DOE, Professor Jianchuan Chen, Temrat Gezehey, Catherine Keski, Rebecca Riles. We were also very lucky to have fantastic postdocs. We have Dr. John Gombe, and also now Professor C. Gao at the very end. She's now at the CSU Sacramento. She was a postdoc here. And we had a fantastic group of graduate students, many of them which part of their dissertations based on some of the results that were obtained in this project. We have Deanne Tuyitao, Mariam Naimatan, Brendan Harrison, Melinda Gonzalez, and Ziad Nazeb. We also have the project involved mobile units. So we worked with industrial collaborators, Professional Traffic Solutions, AC Fox, and Golden State Carbon LLC, in very tough time considering that we had COVID, and for a certain time we just couldn't do any field work. We couldn't even go to our labs. So very, very nice to have a motivated group of collaborators. In outreach, we had Green Carbons Nexus and Butte College, and this is just some names, but there's a lot of people that were basically involved and found out about this project by the outreach tasks that were performed. The whole idea was to do field tests. So some of the field sites were in Bob Kaler's ranch, and we were also very lucky to work with Phyllis Verve dairy, where a lot of the composting and co-compostings were done. We'll describe a little bit better that in the presentation. And then again, we also had to, at a certain points, get large quantities of biochar, and we were able to get it from Agra Marketing. So I'm just going to give a brief introduction, and then each topic is going to be presented by some of the people that were involved. I have to say that we have a very nice collaboration between soil scientists, people like me in the biomass conversion topic. We had some professors doing UAVs and drones. We had the economic analysis. We had the irrigation analysis. We were looking at the project from different perspectives. And what is part of the motivation that we had here? Well, we mentioned that we wanted to do a mobile unit for methane reductions related to agriculture and dairy utilization. But this is a very important thing to analyze here. When we look at these two graphs here, we can see that we have population burden percentile here. So we have certain populations here that are basically affected by emissions from pollutants and transportation issues. If you have dairies, there's odor, things like that. There's methane emissions. In general, there's low income, disadvantaged. They don't have very good access to many times water or some of the health services. If you look at that, and you look at the population and the pollution burden, so you see they kind of align, they're overlapping. So it's this area of the Central Valley where we have that, and we wanted to do something beneficial to them. So if we describe the project has several components, and the idea, one of the areas was the development of field demonstration of a mobile platform for biochar production. We know that because of different aspects, some of the power plants that are related to biomass, they have been decreasing over time in California. Part of it is because of the economics of how much does it cost to produce a kilowatt in those conditions compared to, say, solar or wind, things like that. But also there's the aspect of transportation of the biomass to a centralized area. And we wanted to look at what would it take to actually produce biochar directly at the site. That also came with the aspect of, well, we should probably do a cradle-to-grave analysis of collection, deployment, and utilization of mixtures of manure and biochar. Here, we're trying to work with the dairies so that we can actually produce composting of mixtures that are together, the solid manure and the biochar. We have the other aspect related to analysis of biochar manure compost to reduce methane emissions. So how much emissions are reduced by doing the co-composting. And also, once you have that material and you put it in the soil, we also looked at the biochar potential for reducing greenhouse gas fluxes from the soil. This all in the context of benefiting disadvantaged communities. That is a very important aspect of the project. We have, again, I mentioned that we work with a Philip Verby dairy, and you can see this. They have about 3,500 cows. You can see there's an anaerobic digester here, so they separate the solids with the liquid, and then they produce methane for their own purpose of producing power with the anaerobic digester. But there's also these piles of manure, and we were interested in knowing, again, characterizing that as a controlled type of sample, and then seeing how it compares to doing the composting with mixtures of biochar. Ultimately, what we want is to make sure that we're not doing this. So we know that there are regulations that are coming in 2025, which would ban all sorts of open burning. But even if you're trying to do biochar, depending on how you're trying to make it, you can actually pollute quite a bit. And this is not the idea that we had planned. The idea was to actually work in a way that we're not polluting the environment. So going into one of the topics, the part related to the mobile and stationary forms, we looked at a whole spectrum of units that can produce biochar. We're starting here from the very top left with units that cost, say, $200 to make. Anybody could do. It doesn't matter, again, if they're what economics they have in their farm, but they could actually produce biochar with units like this. Notice that there's by using a secondary air section, there's hardly any smoke. There's really no smoke coming out here. So they can produce things, biochar, in a relatively environmentally friendly way. But also, again, we work with developers. So AC Fox here, we have the 1X machine. This is a machine that, although it's batch, but it's also tumbling. So it's rotating. And then they keep adding until you get to they add material until you get to the amount that is needed. This one, again, part of some of the results are coming from this unit. If you notice, some of these units are still in experimental form. We were hit by COVID, so after that, the supply chain issues had to be dealt with. We had increases in anything that require machine shop would be expensive. Everything that required materials, metals, and things like that require expensive. So we were hit very hard with that, and some of these ones we were able to obtain results, but they're still in developmental stage. We also did work with a much larger unit. If you notice, these are all mobile units. You can move them. Now, this one requires electricity. This one requires propane or some sort of fuel. So the mobile part of it's in a certain way, you take them to a certain location and you hook up, for instance, propane or electric connection, and you operate there for a long time. And then once you're done, then you can move it. So these two require, again, electricity and propane, so they require an external source of fuel. And this one proved to be a little bit hard to control, mainly because it's a fixed bed being heated up from the inside without access to any sort of oxygen. So we did do a lot of tests with that. We also looked at units like this one, like the air burner. This is a unit where there's a curtain of air that is basically rotating here, forms a vortex, and it basically combusts the volatiles that are coming out. This turned out to be a very good unit in the sense that it can process material at larger amounts. It's very easy and mobile to basically go pretty much anywhere. It's requires very little manpower. I mean, just one person can operate it, and it's also using pretty much just diesel here to move operate a fan that produces the air curtain, and that's it. It doesn't require external fuel. Again, we don't really endorse any sort of brand or anything, but we just report on what we use, and this is one of the units that was used. And also we have here, I don't know if we can see here, let me see, we have Agra marketing where we use some of the commercially available biochar. It turns out that some of these units capacity is sometimes a little bit hard to achieve. If I require, say, 5 tons or 10 tons of the material, sometimes with the smaller units, it's really hard to have them in a reasonable amount of time. So in that situation, units like these ones that are stationary, these are for power production, but then they produce biochar as a byproduct, turn out to be very useful. And then there's also Professor Raya has worked with some of the biochar coming from a different type of unit from Corrigan, but again, it's more like a continuous type of operation. Okay, so some of the things that we looked at is we looked at the consistency of the biochar that gets produced, and we can see that depending on the scale that you're doing that, notice that here this is a very small TLUD unit, and we basically flowing 5 liters a minute of air through it. And you can see that the speed at which the pyrolysis front moves downwards is different than if you actually use, say, 10 liters per minute. Notice also there's a large region here where the temperatures are high, and these are basically just a temperatures of the surface, okay? But we had thermocouples, and you can see that there's temperatures that are going roughly close to 400 degrees. And this is important because as you scaling up, you might be able to, in large units like the power generation units, you might be able to reach a consistency that is very uniform. But there's also aspects of, if you have a very small unit, it's going to be affected by, say, ambient temperatures or moisture contents and things like that significantly. And even if you go to a medium size, like the ones, the zip chart and the 1X, they're still going to be affected. So consistency is an important aspect of the results. We actually, since we are interested in the methane uptake, we did a breakthrough curve for some of these. When we analyzed a lot of different biochars, but here, this is just a summary. And here you have the BET surface area, so the nitrogen adsorption results. And depending on the feedstock and the unit, some of them had very, very small surface areas, while other ones, if you notice, this is the same unit, but different feedstock, you can give you a much larger surface area. We're talking about here meters square per gram. And then again, the one that we utilized for the field tests gave a very large surface area. And when we look at the breakthrough curves, again, we have some of them that are very, very underperforming in a certain way. And the rogue biochar was the one that was able to absorb the most methane. So again, there's certain reasons why we use certain material. So with respect to some of the main results and outcomes, it's important to consider there's batch pyrolyzers, there's continuous units. Some of them work, I mean, we work also with other people that are doing gasification. So different, a wide variety of units that can allow you to do some of this processing. Some units require external fuel, which is going to increase the cost, and that doesn't necessarily produce more consistent biochar in certain cases. This is a lot for the results for mobile units. And then again, fixed bed with no air contact between the feedstock and air led to some hard to control type of situations. Some of the units are affected by strong winds here, for instance, and then ambient temperatures affect some of the operations. So we're looking also at consistency of the products. Again, there's a few other comments here, but I think we'll move to the next topic now.
Okay, I think I'll take over. So my name is Brendan Harrison. I'm a PhD candidate at UC Merced. And I'll be talking about dairy manure co-composting with biochar. So we looked at whether biochar could be used to reduce methane emissions from dairy manure through a process called dairy manure biochar co-composting. And this process of mixing organic waste with charcoal in an agricultural context has been practiced in many areas of the globe by indigenous peoples for thousands of years, but it really hasn't been adopted for use in modern agriculture. So our research questions included: one, does adding biochar to composting dairy manure reduce methane emissions and air pollutant emissions? And we answered this question by conducting field composting experiments on a dairy farm, as well as lab composting experiments. We also asked the question, how does the life cycle climate impact of biochar composting compared to composting or stockpiling dairy manure? And we answered this question by creating life cycle assessment models for these systems. And we also asked the question, how effective is biochar co-compost as a soil amendment? So when we actually use this material and apply it to soil to grow crops. So we answered this question by conducting agricultural field experiments and as well as greenhouse experiments. Next slide. So moving right into our results, the figure on the top left shows cumulative methane emissions over the course of a field composting experiment at a dairy farm. And the yellow line is the no biochar control compost pile, and the black line is the biochar compost pile. And we found that biochar composting reduced methane emissions by 84%. And this is just by adding a relatively small amount of biochar to composting dairy manure, about 6% by mass or 20% by volume. And we also found that biochar composting led to negative life cycle emissions, due in part to this reduction in composting emissions, but also due to enhanced carbon sequestration from the high carbon stable biochar that's added to the compost, and from renewable energy production, because producing biochar can actually also generate renewable energy, which was the case for the biochar we used in this experiment. And so this is an added climate benefit of biochar composting. Next slide. So we also found that biochar composting reduced air pollution and odor from the manure. So figure A in the top left there is the biochar compost pile, and the plastic ring is our gas collar, so we use that to take gas measurements. And figure B is the no biochar control pile. So you can clearly see less flies in the biochar compost pile, likely due to lower odor. And we found that biochar composting substantially reduced hydrogen sulfide and NOx emissions, both by about 70%, in addition to methane emissions. So this could improve local air quality, which could improve farm worker and community health in rural areas, and regional air quality by mitigating ozone and PM 2.5 precursors, and by providing an alternative to biomass burning in the valley. And of course, this could also at the same time help us mitigate global climate change by reducing methane emissions, sequestering carbon in soil, and generating renewable energy. Next slide. So we also tested the biochar compost produced at the dairy farm as a soil amendment at a wheat field, and we compared it to applying biochar by itself or manure compost by itself. And we actually found that biochar compost had superior agronomic and environmental benefits, including significantly higher total biomass and water holding capacity of the soil, and significantly lowered nutrient leaching and soil greenhouse gas emissions. So I think that's all for my part, so I can hand it over to the next person.
Yes, hi. Sorry, I don't know if my video is showing or what it is showing. I'm on my phone right now. I apologize. I'm currently, I don't know. Can you all see me? Sorry. So yeah, we're harvesting right now. We're still working on our biochar portion of this project. So throughout these years, I've been characterizing the biochar, doing scanning electron microscopy, looking at the surface area, the surface roughness. And so like in these images, you can see just the variety of the biochar that we've used in this experiment and how they differ depending on like how they were produced, pyrolyzed. And so that was one of the things that we've been doing. Could you click the next slide, please? I don't know. Oh, thank you. And then also with one of the studies that Brendan was mentioning of the field site. So we are also looking at trying to understand how biochar has influenced the carbon dynamics within the soil. So looking at carbon and depth, looking at different types of quality of carbon. So there's active carbon, which is carbon that's more accessible to microbes that can be more quickly transformed. So we're looking at things like that. And then the next slide, please. And then now we're also doing a greenhouse study, which is where I'm at right now, is we're harvesting the barley. So we did 3 different types of plants, marigolds, tomatoes, and barley, and seeing how all the biochars that we've used in the lab composting experiment, and seeing how it influences plant yields, as well as other soil dynamics. And then, yeah, next, that was all I had. And then if this can go on to the next person. Thank you.
Okay, I think it's my turn. Well, hi everyone, my name is T. Tao. I'm a student with Dr. Timra Geze. And so my portion of the project, so the biochar that I use is all from the 1X mobile unit. So in this particular, when we were studying the unit, we have 7 different biochar that were generated from that unit. All of them were from different feedstock that were made from the local agricultural waste product, you could say. So we have 7 biochar, and so the first step we did is that we want to understand how does this biochar influence, or its potential to influence, soil hydraulic property, which is one of the very important factor in terms of both environmental and agronomic effect. So on that figure, the top figure, we developed the water retention curve for the 7 different biochar, and we could clearly see that different biochar have different potential to retain moisture. And then that is just for the paired biochar. We further did 2 different application rate of the 7 biochar. So a 5% biomass and a 10% biomass application rate. And we see very similar trend that biochar, the same biochar that were shown to increase water retention at the peer level, also increase water retention at different application rate. And then after that, we select the 3 biochar that were most ideal for our incubation experiment. And coincidentally, the 3 biochar, each of the feedstock that were either almond shell, walnut shell, or the almond pruning have a feedstock that was selected for our incubation experiment, in which we monitor how does the addition of this biochar influence soil respiration in a controlled environment over a long period of time. So in this case, we monitor soil respiration for 109 days with 2 to 5 days measurement interval. And from both of these experiments, we see that walnut shell, as earlier was mentioned, have the highest surface area based on our water absorption isotherm method. But at the same time, when we're talking about water retention, biochar that were derived from almond shell have the most influence on water retention. And from a lab experiment, it also have the most influence on soil respiration, which we're highly suspecting that it's relating to the additional retention of moisture and the availability of moisture that is being present for the microbe, allowing them to be active and respire more. Next slide, please. And then the 3 biochar that we use in the incubation experiment, we wanted to see, what if we were to model these biochar, how does it influence different cropping systems that have different irrigation dynamic or irrigation moisture regime. So we did a numerical simulation using the 3 biochar. We did a 20-year simulation of that. The first 15 years was used as a spin-off, and then we analyzed the last 5 years to see its impact on soil hydraulic property and also plant water uptake. And from this experiment, we see again that almond shell biochar has a superior impact on water retention and also plant water uptake. But there's the differences between different cropping systems. So we see a lot of benefit in the system where irrigation is a natural event, so a rain-fed irrigation versus a cropping system that you are constantly applying water to. In this case, we run our model on our irrigated tomato system. In both cases, we see very common scenario where the addition of biochar at a 5% biomass application rate always reduce the accumulated seasonal evaporation. And in the rain-fed system, that impact a lot of the plant water uptake. So it's we have a significantly greater water use efficiency at the same time crop yield for the rain-fed system. But for the irrigated system, it's a different scenario because irrigation is being triggered. So and you have to really consider the benefit in that particular system is not as much, and you really have to consider other factors such as carbon sequestration potential or carbon credit to kind of offset applying a 5% biochar to this system. And this particular work is run on economic review in the Beta Zone Journal. Next slide, please. And then the last project is again the field application, which were already mentioned earlier. In this case, we also did a column study in which we monitor the effect of the 3 biochar that were mentioned earlier. In this case, they were co-composted with fresh dairy manure that my colleague Brandon Harrison did in the lab. And then I used that end product to see what is the environmental and agronomic effect on more control, not a greenhouse study, but outdoor column study. So in this case, we did a fresh market tomato. We measure different aspects such as leaf chlorophyll content, canopy development. We measure greenhouse gas emission from these columns. We collected leachate from the column, and again, all trying to look at what is the positive effect of these soil amendment on both environmental and agronomic effect. We also imposed a deficit irrigation on this treatment, so half of the treatment received 75% deficit irrigation. and then the other half were irrigated at full crop evapotranspiration. So very similar to the field study that was mentioned earlier, we see that the most effect that we observe from this is the decrease in nitrogen loss, so in both nitrate and ammonia form. And also we see that the application of these biochar doesn't, in this particular column study, it didn't significantly impact or increase crop yield, but it sustained the crop yield compared to the control, which is a conventional fertilizer. So there's a positive effect of adding biochar to, or in this case, biochar and biochar co-compost with dairy manure to soil as a soil amendment for the purpose of both reducing your environmental footprint at the same time maintaining or sustaining crop yield. And that is the last of my slide. So I'll pass it on to the next person.
Yeah, I think this is my turn. Hello everyone, my name is Dian. I'm a fourth-year PhD candidate. So my topic is regarding the smart sensing of agricultural methane emission soil carbon content, which is biochar for smart application of biochar. So my job is really focusing on how to apply the biochar into the soil in right time, right amount, and right place. Next slide, please. So that's by doing that, we discovered two powerful sensors, which first one is microwave sensor and another one is millimeter wave sensor. The sensing mechanism behind this is about the microwave and millimeter wave, the wavelength is approach to the object size. That's how we can detect the biochar distribution into the soil. Next slide, please. And so here's the reflectance captured by the microwave and millimeter wave radar signals. Left figure is the time domain signals and right figure is the frequency domain signals. And from these figures, we can see there are different, or we can say is a unique signatures between different biochars and their distributions. By classifying these unique features, we can buy some machine learning algorithms to distinguish or classifying these different biochars and amounts. Next one, please. And we also develop sensing modules by combining this microwave and millimeter wave sensing with Raspberry Pi, which also we refer to edge computing, which have the low power cost. And we can easily carry on this device to the field to do the sensing in real time and in situ. Next slide, please. And so since we already have these two powerful sensors, and it's time to look further for the set-specific measurement for soil carbon content sensing. As for the dairy farms, we apply the digital twin in dairy farms. As we can see from the left corner, we have virtual mapping in dairy, and by generating by our physical models, such as dairy geometric flow models, and also the wind velocities, and also the methane diffusion models. And we also have some sensors to capture those physical methane in dairy farms by UAVs flying towards to those source locations to get those mapping concentrations. Then we feed into this real world data into our digital twin models to enable several applications, such as optimal spreading the biochar to emit those methane emissions. And also we have calibrate our diffusion models and also methane leak alerts. And also we can predict the methane emissions in the next couple of days or a couple of months. Next one, please. And another strategy for the digital twin is combined with the Internet of Living Things. So we believed in the soil, not only the soil carbon decomposition will be affected by the living things such as the insects and also the microorganism. So these parameters will affect the biochar decomposition. We want to simulate this transition or activities of these insects and the microorganisms to simulate those biochar erosion or biochar decomposition into the soil. Will convince us we have better predictions of the soil activities and also the remove the carbon emissions. Next one, please. So to summarize, we can characterize our achievements by three main characters. First is the one about how optimal to add biochar into the soil using UAV and UJV to reduce greenhouse gas. And next one is about how to quantify how much biochar is needed in situ with cost-effective methods with those microwave sensors. And last one, next slide, please. How to measure and monitor decision-making in situ towards soil carbon digital twin management. We have a couple of papers talking about this one. Next one, please. Next slide, yes. So to conclude, to summarize, to our best of knowledge, this is the first time we demonstrate the microwave and millimeter wave signals being reflected by biochar can be used to identify its activities and footprints. We validated our system by conducting real-world experiments and machine learning algorithms. And compared with the traditional method of sensing soil carbon content, the non-intrusive method is less labor-intensive. And our portable mobile devices is easily being equipped on the autonomous drone or vehicle to detecting in large-scale soil with cost-effective way and no negative impact to the soil. And in the future, we're planning to use another powerful portable hyperspectrometer, which the wavelengths between the 300 nanometers to 1,000 nanometers, which combine the UV to NIR near-infrared band to sense the soil organic carbon, moisture, and crops, electrolytes, and so on and so forth. That's our future plan. I think this is our last slides. I will hand over to the next person. Thank you.
Hello, everyone. My name is Mariam, and I'm going to talk about the economic analysis of the project. Our big picture question was that how can the use of biochar in agricultural practices impact farmers and nearby communities? To answer these questions, we break down this question to the smaller parts, starting with what are the costs and benefits of producing biochar using these mobile units, what parameters in this budget can have the greatest impact, and how we can account for uncertainties and lack of data. Next slide, please. So the first step was to create an enterprise budget. We built a budget in Excel. It's modifiable and has been published, and users can modify it based on their project. Here I'm showing two tables of the fixed cost and variable costs that we use in the budget. It includes all the parameters that contribute to the final project cost. Next slide, please. So as I said, we need to account for the uncertainties. Biochar industry, as we know, using these portable units, is a very new industry. So we decided to perform a stochastic cost estimation rather than a deterministic or a point cost estimate. So we report a range of the costs. Here you can see in this graph is the result of our study. It shows that with a 90% probability, the production cost of the biochar per ton would be within $500 to $1,500. This is a good way to show the range of the cost with its corresponding probability. Next slide, please. And the question that comes to mind is that how we can decrease this cost. So in order to know that, we must know what items contribute most to the final cost. So we did a sensitivity analysis and find out the production volume has the greatest effect. So obviously, because the major part of the production cost is the fixed cost, the more we produce biochar using this unit, the more we can decrease the cost, but we should consider the limitation in the feedstock and the capacity of these units. So that's something we should keep in mind when proposing strategies to decrease the cost. Another parameters was labor cost, fuel cost, and permitting cost that has the most effect on the final cost of the biochar production. Next slide. So that was our first project. For the second project, we tried to look at the regional economic impact of the biochar. By regional impact, I mean when we are introducing a new industry or a new facility in a region, there will be some connections and interactions between the different industries. For example, for the biochar production facility, businesses such as transportations, almond farms. If we are going to use almond shells as feedstock, and fuel retailers, they all will be connecting each other, selling and buying stuff from each other. So the cash flow will generated by biochar production will increase people's income, which then result in an increase in the tax. So we can see an interaction within these different industries. So in this project, we wanted to put a dollar value in these interactions. Next slide, please. So to do that, we use in-plant modeling, and we estimated economic indicators such as employment, labor income, value added, and output. And for each of these, we included the direct, indirect, and induced impacts. Next slide, please. So here is some of the result. The economic impacts of biochar production in Central Valley, California is expected to create about 2.39 to 3.1 job years per county per year. These new jobs will directly contribute to the output by about $280,000 to the state economy. So as I said, there will be some industries that indirectly benefit. These industries will include commercial and industrial machinery, repair and maintenance, insurance agencies, and so on. Overall, we are expecting to see a value added of about $100,000, a boost in the economy of the state of California. Next slide, please. So a little bit to elaborate on our result, I'm going to explain a conservative scenario of having only one portable biochar unit in 6 counties that I list here in the Central Valley, and we assume a biochar selling price of $2,500 per ton. So in this table, you can see the total economic impacts of the biochar production in the 6 counties. So we can see a 12 new job years that will be directly created as these biochar facilities in the valley. We also are seeing one indirect employment, which means the job created because of operational purchases within the Central Valley and the state of California. One job year will be supported as by business-to-business transactions. Also, another interesting result is that we are going to see about 4 new employment as an induced effect, which means that 4 jobs years can be potentially supported by households spending their money within the state, and as a result of the biochar production facility. Another interesting number here is the total value added of $2.1 million, which shows the added wealth to the state and the contribution of this new facility in the valley to the GSP, the gross state product. So we also calculated these impacts for each of these counties and the other counties in the state of California. But I'm not going over all of this number, but we see an overall positive impact of introducing a biochar facility in all of the counties all over the state. Thank you.
All right, so that gives a very brief description of some of the results. Because of time, we can go into more details, but there's a lot of products that came out of this project. So we have publications, and we're providing this to the SGC, and also you're welcome to request them directly too. We're going to put them also in a website. There's posters, presentations, and things like that. So I think that's a very important part. Now, before we actually go into the Q&A section, I would like to know, we had the pleasure of working with fantastic people, some of them external partners, some members of the community. I don't know if Juan, Barry, Thor, or anybody, Omar wants to say anything, maybe some of the aspects about outreach too.
Well, thank you, Gerardo. This is Barry Sedlick. I'm with Golden State Carbon. First of all, I want to express my tremendous gratitude to Professor Diaz. You heard the remarkable circumstances with COVID and everything we had to contend with, yet he was able to accomplish all and pull all this disparate pieces together. So he really deserves quite a degree of accolades for the work that he was able to do under extremely challenging circumstances. So thanks to Professor Diaz and the entire UC Merced team who were instrumental in doing this. We were actively involved in especially working at Verway Farms, and Omar can talk a little bit more about that. But we do believe that the benefits to the immediate community in the Central Valley are great in terms of quality of life, the ability to deal with the odors, controlling that circumstance, and the prospective economic value that this provides in terms of new job creation. So overall, we think that this whole project demonstrated that this is a very promising area for expansion. And with that, I'd like to turn it over. Omar, maybe you could talk for a second about your experience with the project.
Most definitely, guys. So from our end, it was quite a pleasure working with UC Merced. You know, we're majorly involved in the dairy sector in California. And on top of that, we're also a part of a big movement with the biogas and anaerobic digester, movement here in California. And for us, the whole methane and emission reductions is a big deal for us, right? We want to make sure that we're doing and trying our best to continue the research and facilitate things for facilities such as UC Merced. From a community standpoint, I mean, it's one of those deals where I live in the city of Chowchilla and I show up to my house and I still smell the smell of the surrounding dairies. And, that's one of those turn off points where you just kind of, you're like, how can we help with this? And just during the studies that we were able to see at our own facility in Madera, we noticed, reductions in odor from the piles that had the biochar. We noticed a lot of additional benefits, such as a methane reduction and stuff like that. So from my end, I'm excited for this. I'm excited for the results that came out of this research, and ultimately, I think we couldn't have done it with such a good team, right? Working with Brendan and the other students from UC Merced, working with Professor Diaz, it was all very comforting, and I think we all went into this with a very open mind, and that's helped us, accomplish what we have so far. So I'm happy. I know the big boss Philip is happy, so we should, from our end, it's all been good.
Laura, you're on mute. Do you want to unmute yourself?
Thanks. I was just going to add on the outreach component through Green Carbon Nexus here that unfortunately, because of the COVID situation, logistically, it was almost impossible to go out to the community and spend much time and have a lot of interaction. But with that said, there is ongoing and it's been evolving based on the the results of this grant. Is we are looking at actually pulling together, and Gerardo and I talked about it conceptually or tentatively, having another UC Merced forum that was based on one we developed about 5 years ago, and then fill in the information based on what this grant has supplied. But it's definitely is leading to ongoing results and interest. So it was very productive grant under adverse conditions.
All right, so with that, we'll move on now to the Q&A section of the presentation. So let me see if I